Hello, this is Jack Jackson. In this video, we're going to be talking about L'Hopital's rule. This rule was first made public in the first ever calculus textbook, and that first calculus textbook was published by Marquis de L'Hopital in 1696. The S is silent in his name. Looks like hospital, but it's L'Hopital. And some people will write that without the S. They'll write it more like this here, L'Hopital. But according to one source I have, this is how he spelled it himself, was with the S. So we're going to use that in these notes. And L'Hopital, like I said, wrote this first calculus textbook. So this is up to this point, before 1696, all of calculus was cutting-edge mathematics research, and so it was in research papers and notes and things that you would have seen calculus. And at this point, L'Hopital tries to write a book about calculus for students, and of course, you know, in the years since, we've had many calculus books. But as sometimes happens in mathematics, you would think that L'Hopital's rule would mean that it's a result that L'Hopital came up with himself, and it certainly did appear in his textbook. But it was actually written by a Swiss mathematician named Johann Bernoulli, sometimes called John Bernoulli. And apparently they reached some sort of interesting arrangement by which L'Hopital paid Bernoulli some money for the rights to include some of his results in his textbook, to publish them. And so this rule has become known as L'Hopital's rule. Now, the Bernoulli family is a pretty interesting family. They included at least 8 very important mathematicians and scientists over about 2 or 3 generations, and including several who made significant contributions to the early development and application of calculus. So the first of these would be Jacob Bernoulli. And Jacob Bernoulli completed his doctoral dissertation under Leibniz, and then he in turn directed the dissertation of his younger brother, John Bernoulli, or Johann Bernoulli. And it's interesting to note that the Bernoullis collectively were amazing. They did an amazing amount of work in a variety of different things, and there are many results in mathematics and science that have the name Bernoulli on them. For example, Jacob Bernoulli did a lot of early work in probability. So there's a Bernoulli distribution and a Bernoulli trial and so forth in probability. That's named after Jacob. Some other things, particularly some things in calculus, were named after John Bernoulli. And they each had several sons, many of whom became famous mathematicians and scientists as well. It's kind of ironic that, I know when I think of this, I kind of don't make a distinction between which Bernoulli did which would totally freak these guys out if they were around today, because some of them were very jealous of each other and of other people. And they kind of started the feud between the followers of Newton over who got credit for inventing calculus. So they would be absolutely aghast at people confusing which one is responsible for which results. But suffice it to say that family was very influential in many areas of mathematics and science, and certainly including the early development of calculus. So the Bernoullis and Leibniz, and also Newton and some of his followers, were very much working on trying to make calculus useful and seeing what we could apply it to. So they kind of looked at it as this, hey, this is this great new tool that we have. Let's see what we could do with it. And so L'Hopital's rule is one example of such a little thing that they can do. And what we do with L'Hopital's rule is we're going to compute the limits of certain functions which can be manipulated to have the indeterminate form 0 over 0 or plus or minus infinity over infinity. So before we formally state L'Hopital's rule and give a proof, let's informally consider the following situation. So we're given functions f and g, which each have a limit of 0 as x approaches a. So the limit as x approaches a of f of x is 0, and the limit as x approaches a of g of x is also 0. And what we're interested in doing is computing this limit right here. The limit as x approaches a of f of x over g of x. And so it has what we call the indeterminate form 0 over 0, meaning the limits of the numerator and denominator separately, considered as separate functions, are both 0. Now we know from experience that situations such as this could have any limit possible. Could be any real number could be the limit, or the limit might not exist. It might go to infinity, might go to minus infinity, or it might not exist for some other reason. In fact, every derivative has this indeterminate form 0 over 0 when you write the definition of the derivative. So certainly we've seen this kind of thing many, many times. So let's look at a graph here that has such a thing. So here's a graph. Let's say the green one is g of x, the blue one is f of x, and notice that they both approach 0 as x approaches, say, 3. So we're interested in this part of the graph right here near the point 3, 0. That's the point A, 0. So let's zoom in on this portion of the graph right in there. And when we do, this is what you get. What does that look like? Well, doesn't it look like two lines? Portions of two lines? Well, actually it's not. They're still curved. One's concave down, one's concave up. They're not straight lines, but they look more or less like straight lines when you zoom in closely. And that's one of our basic properties that we've studied before about differentiable functions. If we take any differentiable function and we zoom in close to a point where it's differentiable, the functions look like they're non-vertical tangent lines. So these are lines that they look like are like the tangent lines. So we say that at least as long as we're close to this point, A0, that each of these lines could be replaced with a tangent line, and it wouldn't look a whole lot different. It would be very close. So we see that f of x over g of x is close to the tangent line. Now what's the tangent line? Remember the point-slope formula of a line? It's the derivative times x minus the x-coordinate. Well, I'm sorry, it's the slope times x minus the x-coordinate in parentheses plus the y-coordinate. That's point-slope formula for the line. But since it's a tangent line, the slope is the derivative at that particular x value. So for some x value near x equals a, then the slope of the tangent line is f prime at actually, that should say at A. Let's fix that. Okay. Well, it's f prime at A, but that's close to f prime at x because x is close to A. And so that we get this. Let me go ahead and write what it actually is. It's actually A here. Let me write what this should be. Okay, now we got it fixed. Okay, so it's the slope at the point A, which is f prime of A, times x minus A in parentheses plus the y-coordinate. Now the y-coordinate is 0, the x-coordinate is A, because it's this point A0 on the x-axis. Similarly, the denominator is g prime of A times x minus A plus 0. Now, it is extremely important that this limit is 0, or that this point that we're centering at, the tangent line, is on the x-axis. Because when those zeros, if it was some other number, this x minus a would not be a factor. But with those being zeros, they could be ignored, and we're to this next expression here. But now the x minus a is a factor, so that cancels out. And we get f prime of a over g prime of a. But again, if x is near a, right, then f prime of x is near f prime of a, and g prime of x is near g prime of a. So f of x over g of x is close to f prime of x over g prime of x. Okay? Under these conditions. What were the conditions? That they both have a limit as x approaches 0, and so we could look at this point a, comma 0 there on the tangent line. Now, so if we sort of take the limit then as x approaches a, these approximately equal to's basically become equal to's. So we see that the limit as x approaches a of f of x over g of x is the limit as x approaches a of f prime of x over g prime of x. And that's basically what L'Hopital's rule says. So here's the formal statement of the rule. Let f and g be differentiable functions and let g prime of x be not 0 on an open interval I that contains a, except that these conditions do not necessarily hold at x equals a, and further suppose that the limit as x approaches a of f of x is 0 and the limit of x approaches a of g of x equals 0. Or it could be that instead of the limits being 0, that the limit as x approaches a of f of x is positive or negative infinity, and the limit as x approaches a of g of x is also positive or negative infinity. They could both be positive infinity, both negative infinity, or one positive infinity, one negative infinity. So f of x, f over g, has the what we call the indeterminate form 0 over 0, or plus or minus infinity over infinity. So it has to have that form, and of course then it must be differentiable at least nearby. Of course, we don't really care what happens actually at x equals a because the limits, of course, don't depend on that. And so then we get the limit as x approaches a of f of x over g of x is the limit as x approaches a of f prime of x over g prime of x. And now we're going to do a formal proof where, at least in the form zeros, if we have the form 0, 0. So let f and g be differentiable functions, and g prime is not equal to 0 on an open interval I that contains a, except these conditions do not necessarily hold at x equals a. That's the hypothesis we're given in the theorem. Now further suppose that these limits are both 0. Okay, so f over g has the form 0 over 0. Now notice that the f values of f and g at x equals a, if they even exist, have nothing to do with the limit. So we're going to define these other related functions to be capital F of x is the same as little f of x for all x's in the interval I, except maybe for a. And big F of x is 0 when x equals a. And similarly, capital G of x equals little g of x for all x's in the interval except for a, and big G of a is 0. So we see that the limit as x approaches a of big F of x is the same as the limit as x approaches a of little f of x, which is 0. And the limit of big G of x is the same as the limit of little g of x, all those as x approaches a, which is also 0. And we see that big F of a and big G of a are also 0. So all those things are 0. So, since the limit and the function values are the same for big F and big F and big G are continuous at x equals a. So that means we can apply any theorems that we might have about continuous functions. So furthermore, f and g, since they're differentiable on the open interval I, they're going to be continuous certainly on an interval from a to x, which is some subset of I. And they're differentiable on that open interval from a to x, where x is any number that will make it fall inside that interval. Now, I think it's the previous video, we talked about Cauchy's mean value theorem. We're going to use that right here, and the main reason we went over it is so we could use it right here. So there exists a number y between a and x such that f prime of y over g prime of y is f of x minus f of a over g of x minus g of a. But f of a and g of a are 0, so f prime of y over g prime of y is f of x over g of x for that particular x. Now, we can do there's such a y exists no matter which x we pick. So if we let the x now approach a from the right, the y being between a and x must also, by the squeeze theorem, it's got to also approach a from the right. Okay? And so we end up having, if we take the limit as x approaches a from the right of f of x over g of x, it's the same as the limit as x approaches a from the right of big F of x over big G of x which by what we just said is the limit as y approaches a from the right of big F prime of y over g prime of y, which is, we might as well say it's the limit as y approaches as x approaches a from the right of f prime of x over g prime of x. And that's going to be, let's say that limit exists in some number L. Okay, and if you go through similar steps, but you go from the limit from the left side, you can also show that the limit from the left is the same L. So that proves L'Hopital's rule if A is a finite number, and we have the form, indeterminate form 0 over 0. Now if A is plus or minus infinity, L'Hopital's rule still works as well. What we do to prove that is we do a little transformation here. We let t be the variable 1 over x. Okay? And note that as t approaches 0, x then approaches either positive or negative infinity. Okay? Or at least from one side, it approaches positive or negative infinity. So in this case, here's what we have. We have the limit as x goes to either positive or negative infinity is the same as t going to 0 from, at least from the correct side, of f of 1 over t over g of 1 over t. And we multiply top and bottom by minus 1 over t squared. We take the derivative of the top and bottom. The minus 1 over t squared is the derivative of the inside, using the chain rule. So the derivative of this is like well, it's actually f of x. Derivative of f of x with respect to t is f prime of x times the derivative of the x. Derivative of 1 over t is minus 1 over t squared. And the same thing works on the bottom there. Now, these two things here are going to cancel out because they're exactly alike. Okay? And so we have the limit as t goes to 0 of f prime of 1 over t and then over g prime of 1 over t. But both of these things now switch back to x are here. So if you notice what I did when I went from the first expression to the second one, I just did a substitution. When I went from the second to the third, I used L'Hopital's rule because now I used the version that we've already proved, where the a here is 0, which is finite, and we used that. Then we did some simplification here, cancellation property for the of fractions, and then we just basically did some substitution back in. So we proved this. L'Hopital's rule works if f over g has the form 0 over 0, and this limit actually exists as a real number, but the a could be a specific real number, or it could be infinity, or it could be minus infinity, and we proved that. It actually turns out that L'Hopital's rule works a little bit more generally. You notice it also works if you don't have this condition that both limits are 0. In other words, if you don't have the form 0 over 0, but instead you have this condition so that you have the form minus infinity over infinity or infinity over infinity, and the conclusion is the same. And they both also work whether you have form 0 over 0 or infinity over infinity. This limit on the right if this limit on the right exists, then the limit on the left exists, and it's that same number. But even if the limit on the right does not exist, but say it approaches positive infinity, then the limit on the left also approaches positive infinity. And likewise, if the limit on the right approaches negative infinity, then the one on the left approaches negative infinity. I didn't prove all those cases, but it actually does work out as well. Now, a couple of warnings, okay? It's very important before you use L'Hopital's rule that you check to see that you have the form 0 over 0 or infinity over infinity, plus or minus infinity over infinity. You have to check that, and you have to have that form, or you can't use L'Hopital's rule. More generally, with any theorem, if you're going to apply the results of that theorem, the conditions, the hypothesis, the conditions that you're assuming for that theorem must be true before you can apply it. So, as always, you have to check that. Now, there are some other forms we'll see in the subsequent videos, such as infinity minus infinity, 0 times infinity, 1 to the infinity, infinity to the 0, 0 to the infinity. These are also indeterminate forms, and they can often be manipulated to an expression that has the form 0 over 0 or plus or minus infinity over infinity. But you cannot use L'Hopital's rule directly in those other forms. They must be manipulated first to have the form infinity over infinity or 0 over 0 before you can apply L'Hopital's rule. And then second warning is this is not the quotient rule. In L'Hopital's rule, what we're doing is we're trying to find the limit of a quotient, and we do that limit of a quotient which has form 0 over 0 or infinity over infinity, and we do that by taking the derivative of the numerator and the derivative of the denominator as separate functions. Notice this is not at all what happens with the quotient rule. The quotient rule is to be used when you're taking the derivative of a quotient, okay, which is something completely different. So be sure when you need to use the quotient rule, apply the quotient rule and not L'Hopital's rule. And be sure when you need to apply L'Hopital's rule, you apply it and not the quotient rule. They're different. So this gives us a nice little practical rule or technique for finding certain types of limits. In the next few videos, we'll look at several examples of using L'Hopital's rule.